first speaker tonight is going to tell us how the actual physical practice of architectural design is changing, how digital fabrication and robotic manufacturing are broadening possibilities for architects, and how that's improving the buildings that are being constructed today. Brady Peters came up through Foster and Partners, the firm led by the Starchitect, Norman Foster. There, Brady was part of the group that worked on putting the most advanced computational technology in the hands of designers and architects. He has a PhD from the Center for Information Technology and Architecture at the Royal Danish Academy of Fine Arts, and today he's an assistant professor at the Daniels faculty. So please welcome Brady Peters.
Good evening, ladies and gentlemen. Thank you very much for the introduction. Let's see if this... So this is the new South Harbour School in Copenhagen, Denmark. 3 concepts drove the design of this building. The first concept is building as landscape. Students can walk continuously from the harbour all the way to the top of the building through different types of play, learning, and social spaces. The school is home to 850 students and staff. The second design concept is building as city. The generous common spaces not only connect to the surrounding neighborhood, but these spaces are imagined as city streets themselves, with the vibrant sights and sounds that go along with that. The third design concept is flexibility of use through diversity of spaces. The differently sized, variably open spaces reflect a flexibility in pedagogy that places every child at the center of their own learning. However, open plan arrangements pose significant problems in terms of sound. Scientists have found that poor acoustics and noise negatively impact learning, cognitive processing, reading, attention, concentration, and memory. And this has led to the creation of building codes and acoustic performance recommendations for teaching spaces. Meeting these acoustic requirements has often meant a return to cellular organization at the cost of pedagogical innovation. The South Harbour School combines aspects of both cellular classrooms and open plan learning areas. The school was designed by JJW architects who have had a long-standing interest in sound and architecture. The architects describe their acoustic design concepts in terms of different interior soundscapes. For example, they use words like cocoon, grove, and crossroads. Here, sound is more than simply a functional aspect of architecture. Sound is part of the quality of architecture. Architecture is most often thought about in terms of its visual character. It is discussed in terms of form, symmetry, proportion, and order. Architectural styles are defined by historians in terms of visible features, and architectural discourse is communicated through drawings, plans, and photographs. However, architecture is more than just its visible characteristics and should be judged by its perceptual features, by its atmosphere. Pritzker Prize-winning architect Peter Zumthor describes the experience of architecture as the magic of the real, and he presents sound as an important, if often forgotten, aspect to the creation of architectural atmosphere. Architecture is a field of design dominated by the visual. Traditionally, the tools of architecture are the pencil and the pen, the drawing, the drafting board, the scale model, and even now the computers that architects use are basically virtual drafting boards. So the tools of architecture are noticeably silent. Architects need design tools for sound. And what I'm going to talk about today is how computation will now enable us to develop these tools. So with the widespread adoption of computer-aided design software, architects now regularly create detailed 3D models of their projects. And scientists and engineers have developed computer simulation software that uses these architectural 3D models to predict acoustic performance, and the results can be visualized in many different ways. In the school project, we were able to use our 3D model, analyze it using acoustic simulation to make sure that it met our design goals in terms of building code and soundscape aspirations. Similar to tuning an instrument, architects can tune acoustic spaces. However, a building, unlike an instrument, does not make sound. A building is a modifier of sounds. It shapes the sounds that we make. So this is Norman Foster's sketch for the new courtyard of the Smithsonian's National Portrait Gallery in Washington, D.C. His concept was for this gentle, fluid form of an efficient diagonal structure that would bathe the courtyard with natural light. One of the challenges with designing these large performance-driven projects is not just how to draw them and model them, but also how to incorporate all of these different forces that are acting on the design. To meet this challenge, architects are using computation to create flexible models that incorporate performance analysis. I wrote a computer program that generated the entire courtyard enclosure. The script generated 120,000 unique elements. It was controlled by a set of parameters and a few simple pieces of input geometry. Once that algorithm is defined, changes to the design can be made easily. And as each new model takes only seconds to generate, a large number of different options can be explored. The computer program also generates multiple representations of the building simultaneously, all in sync with each other. For this project, architecture, structural, fabrication, and acoustic analysis all played central roles in the design development. And the digital model, sorry, this is not working. So the digital model essentially became a synthesis of all the different stakeholder inputs. The new courtyard is one of the largest event spaces in Washington. To hold gatherings, speeches, and concerts, the acoustic performance of the space needed to be specially considered. Without any acoustic absorption, the reverberation time would be 8 to 10 seconds. That was a little bit quiet, but that was an oralization, a digitally produced simulation of what the courtyard would sound like without any acoustic absorption.
The Athenian agora was not slow. It was during the 5th century before Christ that the Athenian agora began to take shape as a conversion of the Sphinx and her lattice.
And that's the oralization of what it would sound like with absorbers. So there it had a reverberation time of only about 2 to 3 seconds. But the question is where to put the absorbing material. The floor is stone, the walls are brick, and the enclosure is made of steel and glass. The answer that the architects came up with was to place the absorber in the beams themselves. So here we see a cross-section of one of the beams. The steel structure is in red, and the acoustic absorbing material is shown in yellow. A mock-up was tested in a laboratory where they tested the build-up for its acoustic absorbing characteristics. Those measured parameters could then be used in the computational model to calculate the acoustic performance of the space. To tune the space then, the depth of the beams could be changed to increase or decrease the reverberation time. In the Smithsonian courtyard, the acoustics were tuned through the manipulation of material and form. We know that we are in architecture when we hear our voices returned back to us. When we call out, it is architecture that answers our call. We understand architecture as much by its echo as by its shadows. However, it is more than material that impacts acoustic quality. Through modifying the geometry of the surface, architects can further tune what we hear. This is the ceiling of the Sagrada Familia, designed by Gaudi. And one can imagine that the sound of this geometry would have a much different character than either the Smithsonian Courtyard or the South Harbor School. Mark Burry, a digital design pioneer, has been one of the chief architects of the Sagrada Familia for much of his career. Mark has been exploring the hyperboloid form as a way of describing the complex geometry of Gaudi's designs. While the construction of the basilica began in 1882, the interior has only just been completed, and musicians who have played there comment on a very particular acoustic characteristic. And so thinking that this had something to do with geometry, Mark posed this question to us: what does a hyperboloid sound like? So when the Design Hub in Melbourne, Australia was completed in 2013, we had the chance to investigate this question and prototype a new type of meeting room. Our prototype meeting room, which we called the Fab Pod, the room had an irregular overall geometry so that room resonances wouldn't develop. It had a regular surface geometry to reduce flutter echoes, and it utilized a cellular construction method which enabled the placement of different types of material where they were acoustically needed. When sound hits a surface, three different things can happen. It can either be absorbed, reflected, or it can be scattered in many different directions. While the mechanisms of absorption and reflection are relatively well known, the importance of sound scattering is still to be fully understood. Now, while conceptually and computationally, sound is often abstracted as array, in fact, sound is a wave phenomenon. And in the FabPod project, I developed some computational tools to actually visualize sound waves. What we see here is a demonstration how flutter echoes develop between parallel walls. However, through using a surface with complex geometry, these sound waves are broken up, both spatially and temporally. Come on. Oh, sorry. So this is the exterior of the Fab Pod. Its absorbing surfaces contribute to the acoustics of the open plan office in which it sits. This is the interior of the Fab Pod. Three types of material make up its surface: felt, metal, and plastic. The space sounds lively and diffuse. So what I have shown today is that through computation, architects can now design buildings with complex geometry and output many different types of building information. Also, through computation, architects can simulate acoustic performance and use this information to tune the spaces they design. So the question is, what sounds do we want? And what forms will these sounds take? Thank you very much.
Thank you, Brady. I really need one of those Fab Pod structures in my loud open plan office, I think. And actually, in the last couple of years, I've come across a lot of stories about technology and audio. For instance, we looked at two researchers mapping the acoustics of ancient Byzantine churches with an eye or an ear to creating an acoustic museum. But in particular, we've seen lots of development in artificial intelligence and audio. As you probably know, there's been huge advances in AI for image and speech recognition, partly thanks to work here at U of T, but sounds less so. Noises less so, and that's starting to change, developing AI systems that can recognize different sounds using the same approach to machine learning that fuels image recognition. You can imagine the potential for use in smart homes or in urban environments.